War Thrills in Peacetime by Donald B. Phillips, published in the September 1928 issue of Popular Aviation. It was as if an anti-aircraft shell had blown the airplane's engine to bits. As the propeller burst, 20 whirling tons of centrifugal force ripped, shattered, and tore shaft and cylinder, crankcase, and rod. Only the instinctive reactions of the dazed pilot brought the aircraft under control. A minute before, the two flyers were speeding along just under the damp gray clouds. Not far below, the long billows of the slate-green Atlantic moved slowly and towards the dully, smudgy Delaware shoreline. It was very definitively dirty weather. Stray drops of rain whipping across the windshield had clouded the goggles of the pilot crouching behind it. Intent on reaching an airdrome before the fog could close down, he peered intently through the mist, while his passenger in the rear seat humped over half asleep. Suddenly, chaos and blindness, crashing roar, a sense of shaking, tearing disintegration of the very vitals of the airplane, a stifling odor of heated oil, a strange, unaccountable weight on the control stick. Through a dense burst of smoke, objects barely recognizable as bits of smashed engine were glimpsed in flight. The roar passed, snatching away with it the comfortable purr of the engine. Emerging from the smoke cloud, with faces and goggles streaming with oil, and only the faint whistle of the wires sounding in deafening ears, they planed helplessly towards the water. As they neared it, the pilot pulled the control stick back. The ship plumped in with a blinding burst of cold salt spray, bobbed up, and floated tail high. A friendly fishing boat picked up the airmen and landed them safe and sound ashore. Their telegram to the headquarters of the Army Air Corps set many wheels in motion. It was not the first time that one of the new metal propellers had burst in flight and torn the engine to bits. Something had to be done to keep such accidents from marring the splendid record of accident prevention that was being established by the Air Corps. To understand what was done, one needs to know what a propeller is and how it works. Of course, everyone knows that the propeller is the thing at the front of the airplane that goes around with a loud noise and blows dust in one's eyes as the machine turns around for the takeoff. But there are other viewpoints. To the pilot, the propeller is the thing that the mechanic pulls to start the engine. Once started, its speed lends invisibility, and he does not think of it again until his right leg becomes numb from holding the rudder bar against the unbalanced pull of the swinging blast of air that comes back from the propeller and is called the slipstream. To the mechanic, the propeller is a treacherous beast that is always ready to leap from his hands and shatter arm or leg incautiously put in its path. And the leash, upon which he must depend for its restraint, is a slender ignition wire running to the switch controlled by the pilot as he sits in the cockpit. Even when the switch is off and the engine is cold, experienced mechanics do not stand under the propeller, for this is unlucky, like walking under a ladder. To the surgeon, the propeller is a huge whirling invisible cleaver that can amputate limbs more quickly than he, though not so neatly. Cases are on record wherein individuals have committed suicide by throwing themselves into propellers of airplanes standing on the ground. A quick death, but rather messy. To the aeronautical engineer, the 1,000-pound forward pull of the propeller is like a sum of money that must be stretched to cover more than it can possibly buy. This pull is all that he has wherewith to overcome the air drag of wings and fuselage, struts, wires, and wheels. When the airplane that he has nursed into being from the first rough sketch is at last completed and leaves the earth, every bit of air resistance here and there takes its toll from the propeller pull and holds down the speed. And the cry is always, more speed, more speed. How many laymen have any conception of the days and nights that the engineer slaves at his drawing board, scheming how to eliminate this part, how to pare down another, how to squeeze something else inside the already overcrowded fuselage, all done that the precious propeller pull may be hoarded for the task of drawing the wings to the highest possible velocity. To the moving picture director, the propeller, commonly called the prop by flyers, is also a most convenient prop in the theatrical sense. The gentleman of short sleeves, reversed golf cap, and megaphone discovered long ago that propellers produce small but potential hurricanes, which can be used to toss things about and produce various novel and striking effects. Hence he has invested in antiquated but still serviceable propeller and engine combinations without any airplanes attached to them, which he calls windmakers. These are placed just outside the field of the camera. A few shovelfuls of sand tossed into the air blast create a howling Sahara storm. A fire hose turned into it produces a tropical cloudburst illustration. or by substituting a garden hose, the scene may leap the seas and land in a driving spring shower in some temperate climate. Until recently, virtually all propellers were constructed of wood, and failures through bursting in the air were almost unknown. The air screws used in the great fleets of planes employed in the World War were made of walnut, birch, mahogany, or other wood, and were very trustworthy. They broke if the blades hit chunks of mud thrown from the wheels while rolling, but rarely made trouble in the air except in the case of one particular type of airplane, the French salesman, used extensively at the front during the World War. The salesman had a bad trick of breaking the bolts which attached the propeller to the engine. The loss of 1 or 2 bolts did not matter, since 8 are provided, but the bolt end invariably dropped so as to be struck by the whirling propeller, thereby breaking a strip of wood from the edge of one blade. A mere sliver of wood weighing a few ounces, but this small loss of balance between the blades produced surprising results. Picture the utter bewilderment of the inexperienced Yankee pilot when his airplane suddenly vibrated from end to end like a giant massage machine. The unfortunate flyers, unable to see or think while the terrible shaking continued, felt there was but one thing to do: to stop the engine and land on whatever might be underneath. However, after making a safe landing, correction of the balance was easy. It was only necessary to whittle away the hard wood of the unbroken blade until a piece the size of the sliver torn from the opposite side had been removed. By that time, the hands of the whittler would be well blistered, but the propeller would run quite smoothly, enough to take the airplane to its destination. After the armistice, improvements in airplane design increased the top speed of service-type planes from a scant 125 miles per hour to 150 and more. Wooden propellers will not stand this pace. This fact was recently demonstrated when, due to a shortage of metal propellers, wooden substitutes were tried on certain low-powered but highly refined and fast training machines. Within a short period, 2 of the wooden propellers burst in flight. To be strong, the blades should be thick if made of wood. But thick blades waste too much power when rotated at present-day speeds. At full power, the tip of a modern propeller rotates through the air at a rate of 12 miles per minute, 725 miles per hour. At such speeds, raindrops bite away the wood like bullets. A change to metal had to be made. Steel proved much too heavy, but the newly discovered alloy called duralumin made the change easy, yet brought new problems. Duralumin was just what the word means, hard aluminum. It was never heard of until, during the war, a German Zeppelin caught while bombing London draped its shattered and tangled length across 2 or 3 hills of the English countryside. Pieces sawed from the intricate metal structure were tested. They proved almost as strong as steel and nearly as light as the soft and untrustworthy pure aluminum which was so widely used. Chemists were called upon, and in a day or so they reported the exact composition of the new metal. It was an alloy consisting primarily of aluminum with copper and some other metals added in certain quantities. Every trace of substance which entered into it was known, and it could be easily duplicated, they were sure. A batch of the alloy was melted, casted, and rolled into sheets. It was worthless. For months, experts worked day and night to solve this puzzle and make the new and valuable alloy available to the Allies. It was an unprecedented mystery that confronted the chemists and metallurgists. They could absolutely duplicate the composition of the German metal, but their products were like a different substance, little, if any, better than pure aluminum. They were either soft, brittle, or apt to crumble after a period of use. The final discovery captures the imagination. One can picture the wariness and disgust with which some metallurgist threw the perhaps 10,000th piece of metal on the bench, after testing and finding it as soft and worthless as its predecessor, and his amazed incredulity on returning a few hours later and finding it hard and strong. Doubtless, he first thought it was a practical joke, then retraced his work on that particular piece to see what unusual feature of its manufacture and heat treatment was responsible for the unheard of phenomenon of a metal which on its own accord changed its temper and toughness while simply lying on a bench. The exact steps that led to the final perfection of the process of heat treating duralumin are one of the mysteries of the war, but the process itself is no longer a secret. The aluminum alloy must be kept heated nearly to a dull red by immersion in a bath of melted potassium nitrate for a certain period, then be quenched in a cooling bath. The exact temperature of the potassium nitrate is very important, as a difference of 10 degrees will seriously affect the finished metal. After the quenching, the cooled metal is soft and easily formed into various shapes, but this must be done quickly. For an hour it retains its softness, while mechanics work feverishly to bend, twist, and form it to the exact shape of the airplane part which is required. A short time after an hour is up, It has become strong, hard, and inflexible like a different metal. It must be understood that heat is not applied during this process, and the hard piece is not necessarily cooler or hotter than when it came soft from the quenching bath an hour before. The process described is that employed in the manufacture of ribs, spars, and other light parts of the aircraft, but in making propellers, dies are used to shape the heavier metal to the exact shape desired, which would be almost impossible if it were worked by hand. Shortly after the war, an American inventor made the first duralumin propellers. The experts to whom he submitted his models were not much impressed, but consented to test them. Much to their surprise, these models behaved splendidly when subjected to the destructive whirling test, in which electric motors of many hundred horsepower rotated them faster and faster until the nerve-shattering roar could be heard for miles, and the blades finally tore apart and bit great pieces out of the massive timbers that guarded the test stand. The test rig, as it is called, is a curious device which merits description. The electric motors which provide the power are ranged in line inside a windowless structure unlike any known type of edifice. It is long, low, rounded, of indeterminate color, and appears from a distance to be a huge mound of earth. The roof is of heavy iron. An iron door provides entrance, and the shaft for attachment of propellers projects through one end. Around this end is a shield of very heavy timbers, like a wide arch. Underneath this structure, the earth has been excavated and replaced with massive masonry, which is tunneled with passages and rooms. One of the rooms is directly under the timber shield, and a narrow slot in the concrete ceiling gives a tiny view of the propeller rotating overhead. Through this slot, observers with delicate instruments watch each propeller during test and measure the deflections of the blades as the speed of rotation is pushed higher and higher. A heavy iron shield is provided for closing the slot before the propeller actually bursts. It was soon found that airplanes on which duralumin propellers were mounted were capable of greater speeds than had ever been obtained before, and large numbers have now been placed in use, although they cost more than $400 each, whereas the old wooden type may be purchased for $100. The extra expense is considered justified, as other things being equal, the fastest plane will win an air battle or commercial supremacy, as the case may be. However, shortly after their use became general, trouble developed. The new propellers began to go to pieces in the air. Centrifugal force causes each blade to pull outward with a force of more than 20 tons when the engine is at full speed, although the blade itself only weighs about 30 pounds. This does not cause vibration because each blade pulls against the other, and in manufacture, both blades are made exactly the same weight, tested by balancing the propeller on knife edges so delicate that the weight of a fly would be indicated. Since any difference of weight between the two blades is multiplied by more than 1,000 times by centrifugal force, such slight lack of balance as results from the application of an extra coat of varnish to one blade will produce an unpleasant vibration. If one blade breaks off entirely, the 20-ton whirling pull of the other blade instantly shatters to pieces the light but sturdy engine to which it is attached. The break of a blade may be due to flaws in the metal, since in forging the blades invisible seams are sometimes formed which extend through the propeller from end to end. These seams cannot be detected except by cutting off a piece of the metal, so the problem has now been solved by forging each propeller with a projecting portion on one end, which is cut off from the rough forging and tested. If any pores are found, the forging is scrapped. Most breakages have not been due to flaws in the metal, so much as to what is called fatigue failure, which is explained as follows. All solid metal is composed of tiny interlaced crystals. In fatigue failure, the crystals gradually separate at points where the metal is heavily stressed. Tiny cracks slowly form and run together, and a break eventually follows. Vibration is the great cause of separation of the crystals because of the almost imperceptible but continual bending of the metal which vibration induces. Hence, fatigue failure is frequently noticeable in such thin metal objects as automobile fenders, so often marked with spreading cracks. Wood is immune to fatigue failure, so propellers did not break from this cause until they were made of metal. Duralumin is particularly susceptible to fatigue failure, and the barely noticeable fluttering of the rotating blades is apt to cause tiny cracks after a few million revolutions, and in the course of additional millions of revolutions, such cracks develop into actual breaks. To catch fatigue failure before it becomes serious, it is only necessary to examine the surface for cracks after a certain number of revolutions. For convenience, the inspection is required every 100 hours. Since modern propellers revolve at speeds frequently exceeding 2,000 revolutions per minute, 100 hours of flying is equivalent to more than 10 million revolutions of the propeller. Unfortunately, the cracks are not distinguishable, even with a powerful magnifying glass, without special treatment of the surface. Hence, in the examination, the surface is etched or eaten away slightly with a solution of caustic soda, then brushed with nitric acid and rinsed with water. This causes any cracks which have formed to become distinctively visible. The Army Air Corps recently sent orders to all its stations to etch and inspect all duralumin propellers immediately and after every 100 hours of flying thereafter. As if to prove the necessity of this measure, another accident occurred before it could be put into effect. An airplane was being tested at 200 miles an hour when an explosion-like disintegration of propeller and engine occurred, as in previous cases. The pilot jumped, opening his parachute as he left the ship, which was only 150 feet above the ground. Luck was with the pilot, as the parachute opened before he hit, and he landed safely, while the airplane, speeding without guidance, crashed at the very door of its hangar. Such accidents will not occur in the Air Corps in the future. The inspection by that branch of the service revealed cracks in many propellers, which were immediately condemned. With etching and inspection now required regularly, pilots wing their way, confident that the efficient metal propeller will not run amok and wreck the ship.